Hello everyone, thanks for coming. Today we're going to do a review of our week 12 lecture in the numerical analysis class. So in this week we talk about Fourier transforms and discrete Fourier transforms. First we introduce the trigonometric function or the sine and cosine functions to approximate the periodic functions on the interval minus pi to pi. We can define phi 0 to be a constant 1 divided by 2 square root of 2 pi, phi 2l minus 1 to be 1 divided by 1 over square root of pi sine lx, and phi 2lx to be 1 over square root of pi cosine lx. So we can show that they form a set of orthonormal basis functions on the interval minus pi to pi. For any square integrable function f, such that f is periodic, it can be shown that f has the following Fourier decomposition or the Fourier series approximation: a0 over 2 plus the summation over k for k goes from 1 to infinity, ak cosine kx and bk sine kx, where the coefficients ak is given as 1 over pi, the integration, the inner product of f and cosine kx, and bk is 1 over pi times the integration of f of x and sine kx. So we can also use complex basis functions. So if we are using the complex basis functions, things can be written in a more unified way. E to the power ikx by using the Euler identity is cosine kx plus I sine kx. We can prove that any square integrable function f on the interval minus pi to pi can be written as a Fourier series if f is periodic and the period is 2 pi. F of x is the summation k goes from minus infinity to infinity, ck phi k of x, with the Fourier transform calculated with the Fourier transform for ck. ck is 1 over 2 pi, the inner product of f of x and e to the power ik of x. So here, this inner product is the inner product for complex numbers. U, the inner product of two functions u and v, is the integration of u and v conjugate. So in numerics, instead of doing the continuous space integration, we are doing the discrete summation. So we have the discrete orthogonality. If we are using cosine and sine, then suppose we have equally distributed points xi being 2 pi I over n plus 1, then the discrete orthogonality follows 2 divided by n plus 1 cosine k, the summation of cosine k I times cosine j xi over I is 0 if k does not equal to j, and is 1 if k equals to j greater than 0, and is 2 if k and j are both 0. Similarly, for the summation of sine kxi as times sine jxi, then we have this equality: 2 over n plus 1 times the summation over I of the product sine kxi and sine jxi is 0 if k does not equal to j, and is 1 if k equals to j. So if we are summing over sine kxi times cosine jxi, then the summation is always 0, no matter k equals to j or does not. So finally, we also have the discrete Fourier transform if we are using the complex basis functions. Let m equals to 2l. Then suppose we have n plus 1 or m data points xi, yi. So if we define the function cj e to the power ijx, Pn of x to be the summation over j for j goes from minus L to L minus 1, Cj e to the power ij of x. Then we can show that yi equals to Pn of xi as long as Cj equals to 1 over m, the summation over k, for k goes from 0 to n minus 1, yk times e to the power minus ijxk. So we can also do fast Fourier transform using those complex basis functions, that is to couple the calculation of ck and ck plus l together. Thanks for coming.